we've talked about circuits that have zeros and ones as outputs and inputs. Now let's talk about two other symbols. So, and two other possible outputs. So we have X, which is contention, and notice that we use X also for don't care. So X, we're overloading that symbol, so it depends on the context how to interpret that symbol X. But here we're going to talk about X as contention. So contention is where a circuit tries to drive the output to 1 and 0 at the same time. So the actual value will be somewhere between 1 and 0, and it will be in what's the forbidden zone, which means that you can't interpret that. Who knows what that means? It's not a 1 or a 0, it's in contention. And it could cause the voltage, temperature, or to change, or the delay to change, and often causes a lot of power dissipation. So it could really heat up the wire a lot, and potentially even cause major damage. So here's an example of how we might get contention, where we violate our combinational logic rules and tie two outputs together of these two inverters. One is trying to drive the output to 0, right? This top inverter is trying to drive the output to 0. This bottom one is trying to tie it to 1. And so Y, this output, is contention. And in simulation, X is also used for uninitialized values. And then remember, we use that symbol for don't care. So, so we need to think about the context that we're using to know how to interpret that value. But contention is typically indicates a bug in a circuit, and so we should avoid it at all costs. So contention is not a good thing. And because we use X for different things, look at the context to tell the meaning. Z is used to indicate floating or high impedance. So floating means it's not driven. So we use all of these terms: floating, high impedance, open, and high Z. Those all mean the same thing. So a floating output could be 0, could be 1, could be somewhere in between. It's not being driven. It's like a wire that you find, it's just sitting on the floor. What's that? What's the voltage of that wire? It's not driven by anything. So if someone dumped a bunch of charges on it and then left it on the floor, well, now you get a shock because it does have some voltage, right? So but it's not being driven by a circuit or or some a power source. So a voltmeter won't indicate whether a node is floating because it's not being driven at all. And if you touch the node or your instructor walks over for a checkoff, it may change randomly. So this is actually a bit of an issue because sometimes it works, sometimes it doesn't. If you have like a gate that you've, one input you've tied to A, like this AND gate, and then one you forgot to connect and it's floating, and you're like, sometimes this works, sometimes it doesn't. Well, guess what? You forgot to connect an input. And so that input is floating, or Z. So one circuit that we use that actually we want to have a floating output is what's called a tri-state buffer. And a tri-state buffer is called a tri or three-state buffer because its output can be 1, 0, or a third state, which is not being driven. So when this E stands for enable. When enable is 1, this tri-state buffer acts like a regular buffer. When the input is 0, output is 0. Input is 1, output is 1. But when the enable is 0, the output Y is floating. So we could redraw this. When E equals 1, this circuit just looks like that, the regular buffer. When E equals 0, well, output Y is floating. It's not even being driven by anything. So some uses of tri-state buffers is to drive or to enable what are called tri-state buses. So we could have, for example, a shared bus. A bus is just a group of wires. They're shared by a processor, video unit, Ethernet, and memory. And we put these tri-state buffers on the drivers. So we have an enable 1, enable 2, enable 3, enable 4, and depending on who is driving the bus at any given time, right, anyone can read it at any time. You see these buffers for reading the bus. So all of these units are looking at the wires or the bus at any time, but we want only one driver, right? We don't want the processor to be trying to drive values onto the bus and the video card to be driving values onto this bus at the same time. Now we would have contention. So instead we can use tri-state buffers where only one unit is enabled to drive a value onto the bus at any given time. So if we have the processor's enable 1 being 1, all of the other enables need to be 0. And then maybe later, after the processor drives some values onto the bus, maybe the video card then drives values onto the bus. And so we can use tri-state buffers so that exactly one of the drivers is active at any given time.